Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics.
Welcome to Speaking of Reliability. This is Kirk Gray.
And this is Fred Schenkenberg. Hey, Kirk.
Hey, Fred. Good to talk to you again.
Good talking to you again. Thanks for sending over that draft paper. I thought that was really cool. So when did you first write this thing or run into this?
I believe I first posted it at about 2018. So quite a few years
ago. Almost 8 years ago now.
Yeah. And recently re-edited it using some artificial intelligence that made it much better and much more readable. I have to give AI credit there that they can, will do a lot of good wordsmithing.
That your English teacher will be proud of you.
Yeah. So, and then I sent it off to you, and I've never had it actually officially published in any technical journal. And I have had it on my website, but I'm glad you put it out there because I'd really like to hear people's other engineers in high-speed digital electronics, whether they found this useful. You talked about how you did it and found some in HP, I think, or
yeah, that was years and years ago. And I don't know. And what we're talking about is that, and everybody knows Kirk because he talks about HALT all the time, and finding failures and so on.
Stress limits.
And I have to ask you is, where did you first run into it? But my experience that was similar was at Hewlett Packard is that one of the things that for electronics, especially higher speed electronics, was that the realization that not every chip that you get has the exact same speed. And its ability to, its timing and so on, and its ability to, receive a signal and recognize it. And
right.
Sometimes there's timing delays, and there were stuff that was generally in our guidelines and in our discussions was, and for some teams for the really high risk stuff and where we really wanted it to work.
Right.
Given all that variation, they would have a chip set run, and then they would measure them and get the fast chip, a couple samples of the fast chip and a couple samples of the slow chips in the range that we expected the variation to occur.
Right.
And that was expensive to get one prototype run of a small batch of chips. And then two is to go test them and figure out which ones are high and low, and then keep track of those, so that we build up prototypes with the fast ones and the slow ones, and then add variation to power, add variation to temperature, add variation with the intent to suss out any timing issues primarily. And, if you're only going to wait so many milliseconds for a signal and your copper is not behaving, or your chip is sluggish and getting the word out, or too fast to get that packet out, then it doesn't work. You get missed signals and it has to rebroadcast, and it's still slow propagation, and it can really wreak havoc with the system.
Sure. And it's very hard. These would be soft failures, generally, bit errors and things like that, where you would have it happen intermittently. And that was one of the the only example I had in here in my paper. And let me just kind of summarize the paper a little bit. And the fact that when I was writing my book, I noticed there was a huge dearth, a big gap in the studies or papers or anything that was discussing the variations that manufacturing of the PWBA assembly and components and the actual, in other words, the interface between the hardware and the software and the variations in having effects on the signal integrity and skew, jitter. Since we've been doing, when we were last involved, Fred, I haven't worked with high-speed electronics, but I know they have gotten a lot faster.
Mm-hmm.
The dimensions of semiconductors and actually layouts of PWBAs or actual electronic assemblies like the iPhone are incredibly dense, incredibly thin layers. You're talking about milliseconds. It's not milliseconds or microseconds. It's now picoseconds, and you know, and if you look at an eye diagram of the plus and minus, and I have a little, picture of it, that that's just the little eye in the center of a high-speed digital system that has skew and jitter, and it's just so small between what is considered a 0 or 1.
Yep.
And you're talking about again, semiconductor manufacturers can't necessarily make a particular speed of product of chip for CPUs. That's why they have to, make a big wafer full and test each one with some algorithm that shows that this one can run at a faster speed with less error or,
Yep.
safely. And then so they bend the CPUs based on not on what they can, a whole wafer is going to be one speed. It's not. And so there's always going to be manufacturing in whatever high speed components you have. There's always going to be a distribution of speed. One of the ways you can stimulate the variation that's going to happen is through skewing through the ability of the thermal effects on conductivity and impedance,
Mm-hmm.
that you can, and I show on a Fairchild octal buffer, I show that as the case temperature increases, the speed decreases and the delay is greater. Okay. So obviously, with hundreds of components or thousands of components on a circuit board, these all could have variations that you end up uh, having a poor signal quality, signal
Yep.
integrity. And those are really hard to find. But Allied Telesis, I think it's now called, anyway, over in high-speed switches, that they found some software system crashes by hot and cold and skewing the speed of the systems.
Yep.
And so I just, since nobody looks for this necessarily, and you and I talking about it's the first time I've ever heard anybody talking about using this in the past, but I would think it'd become much more important as the speeds increase and the dimensions decrease in electronics, that these effects at lower speeds, at lower bus clock speeds, uh, were third and
Well, there
maybe
was more
fourth
margin.
orders.
Yeah, there
Yeah,
was way more margin
right.
on the slower stuff,
And new
and
physical phenomena happen when you get
it,
small and higher speed.
well, it's funny. The speeds that some of these things are running at these days is that the basic electronics that we learned way back when, what a capacitor does and what an inductor does and such.
Mm-hmm.
Um, they have different rules now, different behaviors because of the speeds.
Right.
And so a capacitor kind of works like an inductor, and it has all these other parasitics that are now not just little itty bitty,
No.
less than 1% impact now, or like
Right.
10-15%.
Exacally. They really
Consuming a bunch of
become
your margin, and
right.
yeah, it causes problems. The issue is that it's you're talking about it hasn't been published all that much, and I know we've talked about it before. Is Hewlett Packard was not a big publishing house. We didn't. They published some technical papers, but it
Right.
wasn't part of
Right.
that culture. It
Right.
wasn't part of what they did. There were
Right.
certain patents that were filed here and there, and
Right.
but IBM, on the other hand, is their lab and their engineers were publishing all the time. That was just part of their culture, and there was, inside the company, there were awards and bonuses and stuff like that for
Right.
getting published, and it was part of what they did. And so some companies did talk about this, some didn't. The labs like Bell Labs, remember the
Right.
famous,
Yes. Yes.
they
AT&T.
published a bunch of stuff, did a bunch of cool research. NASA might have something on this, but they've tended to use older technology that had more margin right from the get-go.
Right.
And once they
Exactly.
figured out it could survive in space, then they said,
Right.
well, let's not change that.
Right. Yeah, the Mars rovers have had pretty much very established technologies in them, and they're very comfortable with the older, slower systems, and that's fine. But here on the terrestrial Earth, they're increasing the speeds to just I mean, incredibly uh, gigahertz. I don't know, hundreds of gigahertz. I don't know what did the
Oh, the
clock
speeds are
bus.
amazing now. Yeah.
Yeah. So it's just, I know this is something that I've always wondered. And when I did my research for my book, why, with all these knowing the surface roughness of the traces and all that have an effect on each layer, adjacency, layer,
Well,
effects
even the
between
thickness of the
layers,
dielectric makes a
thickness of
difference.
the diet. Right. And that nobody uses, I mean, not only thermal halt, but you would use, like you talked about, doing clock speed variations,
Yep.
you high and low, temperature, clock, voltage. There's a lot of things you could do together, um, after learning the limits of each one, that you could start to really build a in-dimensional space that it's pretty safe and you've got margin on
Yeah.
for all
Well,
corners.
I mean, some of the big chips now, and I did get a chance a few years ago to work with a company that makes the chip design emulators, and they were big
Mm-hmm.
iron. These were, fill your living room kind of size computing systems
Right.
that would take like a week to simulate a modern chip these days. So they
Uh-huh.
would take designs and then run it through this thing and run it through its paces, kind of running it, simulating powering up and having it function, and then
Right.
loading it up in various ways.
Uh-huh.
Um, most of it was just functional checks. It was like building a prototype breadboard of your circuit and seeing if you're
Right.
getting the right voltage at this point
Right.
and another. Now
Right.
it's way more sophisticated than that, and mimicking a billion transistor chip
Right.
is no small feat.
No, it
So
takes just going through all the routines. I mean, I think there was, 20 years ago or something that Microsoft, or I mean, Intel had a real problem with its Pentium processor or something like that. It was found out by the floating point error kind of thing, but
that
it
was
took
more than 20 years ago.
maybe. But
Yeah, I
anyway,
remember that. I was on a
yeah,
Microsoft. It
yeah.
wasn't even DOS 3 yet.
Yeah. So, it just takes a tremendous amount of time to test the matrix of how all the possible, uh, you know, functions of that chip. I mean, it just,
It's
it's so,
amazing what they can pack into these chips these days.
yeah,
But
right.
you're right, is that all the permutations of, because sometimes if you run
Yeah,
two functions that happen to be parallel to
right,
each other, they crosstalk.
right,
And
right,
and then sometimes there's three, and the dimensions are getting so small and the frequency so high that it's like you got a whole pile of really small nanometer size antennas.
right,
It's not really just a wire anymore.
right,
It's not really behaving like it would on your transistor radio back in the 60s.
right. The physics, I mean, yeah, the actual physics changes how how it behaves as you get tiny and tiny. And I can't wait until they have a four molecule, 20 molecule, and it's almost getting there. Uh, Metallization line, or something
Oh
like
yeah,
that.
yeah, they're
It's
down into the atom size now. Can we
Oh
get these
yeah,
gold atoms to line up in one line? There we go.
exactly, exactly. So that's it's going to be really critical that they have some margin on that.
Oh yeah, and you can see it already. Is that somebody's? Oh, I can repair that, and they get out our soldering iron.
Yeah.
I don't think
I
so.
don't think so. That's what's funny about the right to repair. Oh my God.
Yeah, good luck
Anyway,
with that.
yeah.
Yeah, but anyway, I'm really curious of the high speed stuff is changing so fast, and that might be part
Right,
of why we don't get a whole lot of because if you're a company and you spot a problem in a way to detect it, it just is a way to let your competitors know how to improve their product. So I think
Exactly.
there's some of that going on.
Of course, nobody publishes to their competitors how they their best test methods.
Oh,
Okay,
but
it's
we
just
do.
yeah, yeah. And the point you were bringing back about HP9, a lot of engineers just don't have the time nor
Yeah.
motivation to go tell the world about this, and they're
Yeah.
happy that they showed their company it. And I'm just hoping that this opens the minds and they start looking at this is a regular benefit or potential tool to as the clock speeds keep increasing and the dimensions keep falling and new phenomena happen because of that that they can do some skewing and to remember that um, uh, electrons change their speed at different temperatures
Different temperatures
through
and
the
different
materials
behaviors and stuff. Yeah.
and also expansion and contraction and the
Yeah.
spacing between those changes just slightly, but you're going to have that slight variation in a normal manufacturing environment. I mean, hopefully it's all very tight and all your CPKs are really high and whatever.
Well, I mean, this is just one of the other many sources of variation. We're pushing
Right.
into boundaries where the variation's always been there. Now it
Oh,
matters.
sure.
Is the
Right.
difference between a up or a down signal or a 0 or a 1 is
Yeah.
getting so small. And,
Right.
if that 0 or 1 flips at just the wrong spot, then I have an extra $1.50 in my checking account. And that's kind of frowned on, apparently.
Right. Well, hopefully it's also not your car and
Instead of a left turn, it goes right turn.
Yeah, exactly. Whatever. So yeah, it's something that again, it would be great to hear other people's experience and the only one that has uh actually published it and it's a paper I document from a company formerly called Allied Telesin, and it was in
Tellison or Teledyne?
no Telesis. Now they're called Allied Telesis,
Telesis.
and
Okay.
they're in New Zealand. I think they're high speed switching
Okay.
systems, and I show an abnormal LED system crash, and all these were because they were going to hot and cold. They were seeing these happen, and I think that that's these since nothing it was a hard failure. It sometimes are ignored. I think that unless you get it to be catastrophic or something like that, where you can actually study it. But they were able to fix it and correct it through this kind of thermal. Well, the benefit of temperature use in halt, and I'm sure probably did some bus variations, some clock speed variations too. I don't know all the details, and of course they don't always publish all the details, but
Yeah. Yeah.
it is a useful potential tool that I don't see anything, and I haven't seen anything even recently in Google Scholar or any place where I've looked at the effects of temperature and PWBAs and signal integrity. It's just nothing out there. And I
Yeah.
went talked to Sam Keene, who was head of the Reliability Society at one time, in IEEE, and he was also a specialist in software reliability, and he hadn't heard of anybody doing a lot of work on this. So that's why I wrote the paper and
Well, I'm
published
glad you
what.
did.
And
So
I
it's out there, and obviously, since Kirk's doing the notes, he'll add a link to it, right, Kirk?
Yep, you
For the
bet.
paper. Like, you're good about doing that.
Oh yeah.
And so you can take a look at it, let us know what you think. And if you have any good questions about it, give Kirk a call. Don't call me. Call Kirk. Give him a shout and see
Yeah,
what
love
and
to
let
talk
him
to
know
you
what
about
you're
it.
working on or not working on, or if this is a new idea, or if this is, you've been doing it
Something
for
you've been doing, yeah.
doing all along. That's great. Compare notes. That would be great. And that's kind of the idea of getting this out there, is that it's
Right.
one of the many ways that we share information with each other.
Well,
And
that's what's
so,
great about Exendo Reliability. Lots of really good articles, information, and really kind of covers the scope of all kinds of reliability from pre-market to aftermarket and even the plant maintenance.
Yeah, all kinds of good stuff. So if you're listening to this and got it or intrigued by the idea, take a look at the paper and give Kirk a shout to, what you think. Or if you've got another, is anybody working on fill in the blank? Let us know.
Yeah.
If you've heard of it, or we can find somebody that has, or might be an area that we could say, hey, we need to work on this, do something with it. Let us know. Head over to accendoreliability.com/go/SOR. There's a couple of ways to get in touch with us. Actually, Kirk, I don't think I told you is that somebody actually used the speak pipe the other day. It's our second voice message. So Carl and I recorded earlier this week a couple of podcasts based on a really interesting question that we got an audio clip from, a voice message, basically. That was pretty cool.
Did you put it in the podcast?
Yeah, that's the plan. Is we're going to add the recording to it, so you can hear the question for yourself and see if you got it wrong or not. If you'd rather write it down, that's fine. Kirk and I and the other hosts of the show are available through LinkedIn and our About pages. So plenty of ways for you to get in touch with us. And don't let any signal integrity get in your way. Use the low bandwidth method if you have.
Just run slow.
There you go.
Okay.
All right, Kirk, thanks so much.
Okay, Fred, we'll talk again soon.
All right, take care.
Bye.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.